All right, guys, welcome back. What I'm going to try to do today is take a little look at condensed structures and line structures. So these are two things that we're going to have to do in organic chemistry because at the end of the day, organic molecules can be big and they can be complex. And writing out full Lewis structures all day long is really going to be too much of a time sink, and we have to learn some way to make that a little bit faster. So again, the two things that we're going to try to accomplish today are Lewis structures and condensed structures and Lewis structures. And so what I'm going to do right now is flip on over to my screen, and we're going to think about how we can do that, okay? And so that screen's going to pop up here in just a second, and then we'll go from there. All right, so let's start off first with a condensed structure. So one of the important parts about a condensed structure the important part is that it has all geometric information. Forgot my N. So it has all geometric info. And so what that means is that the condensed structure is a way to look at the molecule without having to write down every single bond, but still contain all the geometry and all the geometric info. And what that means specifically is it means the connectivity. So we want to look at the condensed structure and how it conveys connectivity without drawing all the different bonds out. Now, here's a little disclaimer. At some point, you're not going to be able to draw a condensed structure with more complicated molecules. It's just not going to be possible. But for some of the smaller and medium-sized molecules, it's going to be, you can do condensed structures, and it's definitely commonly used. And so, we want to kind of get a handle on that. So let's take a look at something like, let's take a look at methane. And so what I want to do is first I want to just start out with this Lewis structure and show you what we could do to sort of make it a condensed structure. Well, if I were to write CH4, which of course is the formula, then at the end of the day, that's sort of a condensed structure. It does really have all of the connectivity information. You've got a carbon connected to 4 hydrogens. Now, at the end of the day, we want to think about larger and more complicated molecules. So what if it was ethane, CH3 group connected to another CH3 group? Well, what would that condensed structure look like? Well, I would simply write out CH3 connected to CH3. And so that does have the information about how that thing is connected. But what if I extend this out a little bit further? Well, what's this group then? This group is a CH2. It's connected to a CH3 on one side, and it's connected to a CH3 on the other side. And so this is the condensed structural formula for propane. So do you see how this is much faster than writing down every single bond? And so let's think about this now. What if I take this thing, I'm going to continue to add a few groups at a time, and let's see what happens. So CH3, CH2, CH2, CH3. And of course, I spread it out a little bit. You would try to put those closer together, but I was at least trying to illustrate how those things are connected to the Lewis structure. And so if you were writing it down on a piece of paper, it would all be put together like this. All right, so let's take something and let's make it actually fairly long. Let's take CH2, 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 and now let's put a CH3 at the end. Well, what we might end up doing with this structure is we might end up saying, I've got a CH3, it's connected to some CH2 groups, and how many CH2 groups is it connected to? 1, 2, 3, 4, 5, 6. So what I might actually do is say, look, it's connected to some CH2 and there are 6 of them, and then it's another CH3. So this is really starting to condense the structural formula down. And so when we have something in parentheses, we're saying the group is attached to that many of them. And so let's take a look at how this might even get more complicated. And so if I were to take this molecule, let's condense it down just a little bit. And then let's have some branching going on here. What if I had a CH here, a CH here, and then a CH3. And then let's continue to move on with this one. CH2, 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 CH3. So how could I draw this as a condensed structure? Well, what do I have here? I've got 1, 2, 3 carbons there. I've got 1, 2, 3 carbons there. And so it looks like these are identical. So one way that we could write this structure down is to say, look, I've got a CH3, CH2, CH2. That's what that is, right? CH3, CH2, CH2. And I got another one of those right here. So it turns out that I have 2 of those things, and they're both connected to a CH. Then the CH is connected to some CH2s. How many is it connected to? 1, 2, 3. And then finally, that's connected to a CH3. Now, you can do this same bit of business if you had some double bonds and some triple bonds in the molecule. The only difference with the condensed structure is that if you have something other than a single bond, you want to show it. So if you had something that looked like this, see, now I'm starting to write it a little faster. So then what do you have here? You have a CH3 connected to a CH2 connected to a CH double bond C CH3 oops, and all of that is connected to a CH2 CH2 CH3. Well, why did I put that CH3 in parentheses? And some might even say I don't even need the parentheses there. I could even get rid of it, because there's really only one thing that could actually be connected to. There's only one actual possible connectivity. And that is, look, if I have a double bond, it's got to have 2 or 4 other bonds, 2 on each side, connecting something to it. Well, I've already told you what's on this side. One of the things is an H, and the other things are the CH2, CH3. Well, what about on this side? Well, there's 2 things. There's a CH3, one of those things is a CH3, and the other one is the CH2, CH2, CH3. So that's one way that we can do it. We can do the same thing with triple bonds, and that definitely makes it easier to think about molecules when they're a little bit larger. So I could even go backwards, right? So I could say CH3, 3 of them, connected to a C, connected to a CH2, and then there would be 4 of them connected to a C with a triple bond to another C, connected to CH2 with 3 of them, and then I would have that connected to a CH with CH2, CH3, and 2 of those. All right, so what does this all mean then? So it doesn't really matter where you start. Sometimes it's easier than others to start in the middle. Sometimes it's easier than others to start on the end. I'm just going to start on the end because that's where most people do. I'm going to read it from left to right. So what the first thing I have to say is, look, I've got 3 CH3 groups. So let me write them out. There's 1, there's 2, there's 3. What are they connected to? They're connected to a C. And that kind of makes sense, right? Because a carbon has to have 4 bonds. Well, what is this carbon also connected to? Well, it's connected to 4 CH2 groups. 1, 2, 3, 4. You already see that Lewis structures are a little tedious. We're going to have to do something else here in just a second. What are those CH2s connected to? They're connected to a C that's got a triple bond to another C that's connected to 1, 2, 3 CH2 groups. And then the CH2 group is connected to a CH. And then what is that, the other 2 things that that CH2 is connected to? Well, it's connected to 2 CH2, CH3 groups. And I didn't expand them out there at the end because I started to get a little bit lazy like I did here at the beginning. So that's it for condensed structures. I hope that helps a little bit. This is what you're going to have to be able to go both directions. Take a Lewis structure and make it a condensed structure. And you're also going to have to take condensed structures and turn it into Lewis structures and other types of structures. But let's get down to something a little bit more important. What if I have something like this? Let's take a look at C, 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 C. Let's have a double bond here, a double bond there, double bond there. Let's actually make another C there, another C there, a C there. Let's make a double bond here. Let's make that an H. Got to have 4 bonds, H. Think about how long this has taken me to do this. H there, H there. What if I have an N, H, H, H? That took a little bit of time. What I want to talk about now is line structures. Look how I can draw this same structure with lines. Here, let me erase one of those. This thing has all of the same structural information as the structure on the left. The Lewis structure has the same structural information as the line structure. And so let's sort of break it down and let's see how we do this. And so at the end of the day, look what's happening. Every time there's an inflection point, a place where the line bends or meets, what is going on right there? Well, at each of those spots, there's a carbon. At each of those spots, there's a carbon. And so with line structures, we don't show carbon and hydrogen. We don't show them. We show the hydrogens if they're connected to, we show hydrogens connected to heteroatoms only. And what is a heteroatom? A heteroatom is one that's not carbon. And if it's not carbon, we show it. So that's why I'm showing you the nitrogen and the 2 hydrogens connected to it. The other things are still there though, right? I'm still showing you the bonds, whether they're single or double bonds. Well, what am I supposed to understand about the hydrogens? I'm supposed to understand that they're there. In other words, I always include formal charges. You never leave a formal charge out of a line structure. And the reason we don't do that is because if you do leave the formal charge out, then readers get confused as to what's there. I know that there's a hydrogen here, 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 and that's it. I know that because there are no formal charges on those carbons, and they all have a full octet. So let's take a look at a simpler example, right? Let's take a look at something a little bit more straightforward. And so what happens to something like good old propane? What am I going to do with that? Well, that's a simple picture of propane. So remember that at every single inflection point, there's a carbon. All of those carbons have the number of hydrogens on it that it's supposed to in order to be neutral. 1, 2, 3, 4, 5, 6, 7, 8. And so those hydrogens don't have to be shown in order to convey the structural information. We can continue to get even more complex, right? And so let's do CH3, CH, CH2, CH2, CH3, CH2, CH3. Okay, so what do I have here? I've got a CH3, and it's connected to a CH2, CH3, and it's connected to a CH2, CH2, CH3. So I've shown all of the information that I need in order to convey the structural information of this molecule. I've got how many atoms? I've got 1, 2, 3, 4, 5, 6, 7 carbons. How many do I have here? 1, 2, 3, 4, 5, 6, 7. And so we have to be able to go the other direction as well, right? So we have to be able to take something like this and show what that is to our readers. So this is a CH3, CH2 connected to a C, and that C is connected to 2 CH3 groups, and then it goes on to be connected to CH2, CH2, and then what's here? How many bonds are shown? Only 3 bonds to carbon are shown, so that means that there's another bond to a hydrogen, so that's a CH group. And then what is it connected to? It looks like I've got a CH2, CH3, and there's 1, 2 of them. And so that's how I go from a bond line structure to a condensed structure, or to a line structure to a condensed structural formula. In both cases, they maintain the geometric information and all of the connectivity. This works out the same way for cyclic compounds. So what if I have something like cyclohexane? Well, I can draw cyclohexane in the shape of a hexagon, cyclopropane in the shape of a triangle, cyclopentane in the shape of a pentagon, cyclobutane. What if there's a heteroatom in the chain? Well, remember, we always show a heteroatom. So if there is a heteroatom, I want to make sure to show it. So I have to include it. Right? The lone pair is to be understood. What if I have something like this? 1, 2, 3, 4, 5, 6. Let's show me the OH group. When I think about an atom and on a line structure, remember that the formal charges have to be shown. So what does this mean about the formal charge on this oxygen? The formal charge is 0. Well, what does the structure show you? It shows you that it's connected to some carbon chain, and I usually refer to carbon chains as R groups, and it's connected to another hydrogen. Well, what does it have to have as well as those 2 bonds in order to have a 0 formal charge? Well, it's got to have 2 lone pairs. The same thing is true for doubly bound oxygens. If I don't show you a formal charge, then the formal charge equals 0. So what does this structure have to be in order for the formal charge to be 0 with a double bond. It has to have 2 lone pairs attached to it. Now then, what if I do show you a formal charge? There, negative formal charge. Well, what does that mean? Well, if I show you a formal charge that's negative, that means, well, this one is shown without a formal charge, so it's neutral. It has a 0 formal charge. It's got 2 lone pairs. How does an oxygen get a -1 formal charge? Well, it has to have 1 extra electron. So that means it has 3 lone pairs, including the bond then. And that's what gets you your -1 formal charge. Well, what if I have a structure like this? What if I have something that shows you that there's a positive formal charge? This is a carbocation, and we're going to talk more about that later on in the semester. What's this mean? Well, in this case, this means that I've got a carbon that's connected to 3 other CH3 groups, but the carbon has a +1 formal charge. Well, how does a carbon get a +1 formal charge? Well, it only has 3 bonds. That's how you get a carbon that's got a cationic charge. In other words, if you see a carbocation, it has 1 less hydrogen than it should. So for instance, if I said this was a cation, then the structure at this location is a carbon connected to 2 R groups and only 1 hydrogen. That's where the positive charge comes from. If I show you a nitrogen connected to an ethyl group, an ethyl group, another ethyl group, and I show you a no formal charge, if I just leave it like this, then how is a nitrogen neutral if it's got 3 bonds? Well, if it's got 3 bonds and it's neutral, well, it must have a lone pair there. Well, what if it doesn't have 3 bonds? What if it has a double bond to one of these things? Then what must the formal charge be? Well, here the formal charge will be positive. Remember, nitrogen, oxygen, carbon can't have more than 4 bonds, so there's definitely no lone pairs there. So 4 electrons is what it has. That's what it has assigned. It has 5 from the periodic table, so that leaves you with 1. So the formal charge is +1. So let's do one last little structure. And so how would we draw the line structure of something like this? What if I had a carbon and 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 a carbon? What if I connected it to a nitrogen, which was connected to a hydrogen, a carbon, another carbon, and that was connected together? What if there was a double bond here, a hydrogen here, a CH group here, CH group here, and then a CH group here, and then a nitrogen group with a hydrogen. Oh, excuse me. Let's have this connected to a C, connected to an H, connected to an H, connected to an H, connected to a C, connected to an H, H, H. Phew, look at how, what a pain this is. Look at this. It's such a pain. I'm still not even done. I got to fill in all these hydrogens. Look how long that took me to do that Lewis structure. Let's say we had something like this. Well, how do I sort this out and make it into something that's a line structure? Well, what do I have over here? I've got a 1, 2, 3, 4, 5, 6-membered carbon ring connected to a 5-membered carbon ring, but that's a nitrogen. So I want to make sure that I show the nitrogen. That's there. There's a double bond here. Then that's connected to a CH2, a CH2, a a CH2, and that CH2 is connected to a nitrogen, and that nitrogen has two CH3 groups attached to it. Now I need to come in here and fill in my double bonds. Boom, I'm done. That's it. That's all there is to it. You've done it. See how much faster that was? And so at the end of the day, you must know this. That's your job. So practice drawing line structures, practice drawing condensed bond structures, because at the end of the day, we're gonna be showing that. Oops, got my hydrogen. Forgot my hydrogen. I'm going back to fill in the hydrogen, because remember, all hydrogens are connected. You show all hydrogens connected to heteroatoms. And so I forgot that nitrogen. I forgot that hydrogen. So now it's shown. So now I'm good. You must know this. Bottom line is this is how we're going to do structures from now on. This is it for the rest of the semester and all of next semester. All right, guys. See you later. Good luck.